Hi guys, BuildZoid here, and today we're going to be doing another GPU PCB breakdown. This time we're going to be taking a look at Gigabyte's take on an RX 6950 XT PCB. The pictures are from TechPowerUp's review of this card, so big thank you to TechPowerUp for providing high-res PCB pictures in their reviews. If you want more information about the card, there's a link to their review of it down in the description. There's also other links down in the description that you could check out, which would be much appreciated. Anyway, with that out of the way, let's get into it. Now, I didn't really think I'd be doing a PCB breakdown of this card when I first saw it, because my immediate reaction when I saw it was, oh, it's the same as the 6900 XT that Gigabyte made. Except for one difference, and that difference is rather significant, and also this is the 6950 XT Gaming OC. Just in case Gigabyte has some other variants of this card, though I've only seen this PCB from Gigabyte, so I don't really think any other variants exist. Though Gigabyte might be using this PCB on multiple different, different SKUs. Yeah. Anyway, so there's one difference that led to me actually making this PCB breakdown. And that difference is the power stages being used, because most 6950 XTs and 6900 XTs use Infineon's TDA21472 70 amp smart power stages. This card uses Infineon's TDA21490 90 amp smart power stages, and these are kind of special because these have a sort of expected efficiency curve, or at least on paper they can achieve efficiencies of up to 97% at 1.8 volts output voltage at 600 kilohertz switching frequency. For comparison, most smart power stages that I've seen on motherboards and GPUs ranging from 60 to 105 amps have efficiency curves in their documentation that top out somewhere around the 95% range. For comparison, the TDA21472 from Infineon tops out at 94.8% for 1.8 volts output voltage, 600 kilohertz switching frequency. So this is probably, this is quite possibly the most efficient power stage that you can currently get on a GPU or a motherboard, because I am not aware of any other smart power stages that have performance curves, efficiency curves that hit 97%. Now, obviously, some of that might be down to the test methodologies used by the various manufacturers, but it's still it's a big gap, and this is a lot more efficient than even Infineon's own parts. Like the TDA21472 is not that different from, say, the old IR3555 or the 3575. And so the 90 amp part, this power stage suddenly having a 97% efficiency capability is actually really surprising to me. And there are other 6950 XT PCBs that use this power stage, as well as other 6900 XT PCBs that use this power stage. And it would be actually really cool to see a test of this power stage on a 69 against the TDA21472, because the thing with the 6900 XTs and 6950 XTs is I am pretty sure that there are multiple different cards which have the exact same PCB, but the only difference is the power stages. Obviously, there's Gigabyte's 6900 XT card, which was on the TDA21472s. And so, theoretically, you could do a really, good A-B test of, set both cards to the same power limit and ensure that they're both constantly power throttling, because you really don't want them pulling very different amounts of power. That would totally throw off the results. Since I think this is the exact same PCB, you can use the same heatsink on both cards, you can use the same thermal pads on both cards, you can use, you could do everything the same except for the power stages. And I think that would be a really cool test to do, because it's very rare that you get an opportunity to test, the exact same hardware configuration with just one difference being the power stages. I think that would be a really cool test, especially since these are the only smart power stages that I'm aware of that advertise a efficiency of up to 97%. Again, that is at 1.8 volts output voltage. At lower output voltages, the efficiency is generally lower, but that's true for all smart power stages. And most other smart power stages, are around the 95% efficiency mark at 1.8 volts. So anyway, that's kind of why we're doing the PCB breakdown of this card. Is just these power stages are pretty cool, and that's why we're taking a look at the card. Gigabyte has also made some other adjustments to the card that are a bit interesting. Though overall, if you want like the short version of the video, I would not. This would not be at the top of my list of 6950 XT PCBs. Like, I wouldn't be rushing out to buy one of these. Is what I'm getting at. Like, I'd probably get a Sapphire or an MSI card before I got this. But like the PCB's fine, as we'll see. But I don't consider it like the peak of 6950 XT PCB designs, even though it does use these potentially, potentially the best power stages you can currently get for well, actually, nominally they straight up are the best power stages you can get on a 6950 XT. I just don't know how much of a difference they make in practice, because the numbers you get in the documentation don't necessarily always match the performance that you're going to get in the real world, depending on implementation differences compared to the test setup that was used to achieve those results. Anyway, so before we get into more details on the power delivery, and I've already talked a lot about the power stages, but the card does have some neat features. You get dual BIOS functionality up there, so if you want to mess around with BIOS flashing, you can. Also, if for any reason one of the BIOS chips gets corrupted, which I've personally never encountered, but if something goes wrong with the BIOS chip, you do have a second one, so that makes life a lot easier in that kind of scenario. Now, one of the reasons I wouldn't really consider this a top pick for a 6950 XT PCB is because of the fuse configuration on this card. There's one fuse. We're looking at it. It's right here. Also, I'm pretty sure the Q is 20 amps. I didn't bother to check. It's 20 or it's 10, one of the two. It doesn't really matter, because the important part is this is the only fuse on the entire card, and I am very confused about this, because, I guess they're expecting whatever's connected to the PCIe slot to have a higher failure rate than whatever's connected to the 8 pins, but, why do we not have fuses on the 8 pins, right? This makes zero sense to me, especially since there are other 6950 XTs out there where you can get, I understand when a manufacturer like Asus just doesn't have fuses on their cards because they don't have fuses on their cards. That's just how Asus be. The funny thing is, actually, a few years, during the Fermi era of GPUs, Asus was actually putting fuses on absolutely everything. But yeah, but basically, I think NVIDIA 600 series is around the time that Asus basically stopped using fuses. So I can understand if your GPU has no fuses on it whatsoever. I really don't get what's going on when you have one of them. What is this? Anyway, the point of having fuses on GPUs is that the fuse doesn't prevent the card from failing in an overload scenario, or just if there's a defective component that somehow slipped past QA. That's not what the fuse is for. The fuse is there to basically limit the amount of damage that a failing power delivery component can cause, because if you don't have fuses and you have a power stage fail, it can just blow a hole straight through the PCB, and then that ends up being way more difficult to fix than, well, if you have a fuse and it doesn't blow a hole into the PCB. Now, obviously, this isn't really that important while the card is under warranty, because if the card is under warranty, regardless of how much damage a failing component does to the card, in theory, you should be able to just get the manufacturer to, deal with the problem, and it's their problem how they're going to fix it. But once the warranty expires, having fuses, board protection fuses on GPUs, and, well, I've never seen them on motherboards, so I'm not going to say that they're a thing on motherboards, because they're not a thing as far as I know, but yeah, board protection fuses on GPUs are just a really good idea, because it's going to make if any repair attempt is being made, it's far more likely to succeed if there are fuses on the cards. So I am very confused by there being a fuse here and there not being any fuses up here, especially since like Gigabyte on their like 30 series RTX cards, they have fuses on those. At least a lot of them. I don't know if all of them, but a lot of them have fuses on like all of the power connectors, and then the 6950 XT is like, yeah, the PCIe slot is has a fuse on it and nothing else does. So that's rather strange. And that's basically most of why, like, that's a big part of why I wouldn't really consider this a top pick, because you can get a lot of other cards that have, comparable power delivery, arguably better capacitor configurations, and also all of the power connectors actually fused. So, yeah, anyway, let's talk about the actual power delivery now. So, the VRM layout is typical 6950 XT things. You've got 2 phases of SoC VRM down here. You've got 4 phases of vCore above that. Then on the other side, we've got 1 vCore phase just chilling up on the top edge of the... Actually, I'm just going to put a big rectangle around this whole thing, and then we're going to subdivide that up. I'm going to make my life a lot easier that way. So yeah, but on the top edge, we've just got like a single vCore phase chilling up here. Really not sure why. Like, Gigabyte kind of went to town on modifying the layout of this PCB quite significantly, and it's just like, and then they put the vCore up over here, which is just like, but why? Like, why not put it over here or something? Because like over here they need to like basically, like, over here you have like your memory power plane, of course. Like, your memory power plane goes all the way around the chip, so obviously a lot of the vCore power plane has to go pass under it in this area already. But it's just like, but why would you add like a weird strip of vCore over here? Like, I don't get it. Like, you could have just put it, well, I mean, you'd probably have to extend the PCB a bit, but you could have just put it over here. Oops. Yeah, so I'm a bit confused by why vCore is just sort of chilling up in that area of the card, but this is not the first card we've seen with this. Sapphire did this as well. Below that, we have the memory VRM. Again, just 2 phases, typical 6950 XT things, and then under that we have the VDDCI rail, which powers the memory controller. So yeah, pretty. And then under the rest of this is of course just more vCore. So a pretty typical 6950 XT, 6900 XT VRM configuration, right? You've got the vCore VRM on both sides of the core. This is just to effectively make the power plane cross-section larger, so you have less power losses in the power plane. And arguably this might be part of that, but I kind of feel like this vCore phase is up there just because they didn't feel like shifting the main vCore VRM around or something. Like, they didn't want to redesign the layout of the memory power plane or something, is probably the more likely answer for why there's a vCore phase just chilling on the top edge instead of, I don't know, in a more, like, sensible location. Not that I think this hurts anything, it's just weird. It's just like, there's just vCore. Like, if it was many phases, I'd kind of get it, but it's just one. It really like, it just kind of looks like they were like, we went to 12 phase. Where do we put phase number 12? Well, there's some empty space up over here. Let's shove it up there. Anyway, yeah, so you have the double-sided, well, the vCore VRM from both sides to improve power delivery, yeah, pretty standard 6950 XT VRM layout. In terms of controllers, we're looking at the usual for a 6950 XT. So the main controller is the Infineon XDPE 132G5D, and I've ended up writing over the capacitors again, so, well, I should have put that label over there, but whatever. Anyway, so this is a digital, like a fully digital 16-phase controller from Infineon. It's the best thing you can get for AMD GPUs right now, and here it is running in a 12+2 configuration where, you have 12 phases of vCore and then 2 phases of the SoC VRM. And up over here, so should I even bother with that? Well, too late. There. So it handles vCore and SoC. Up over here, we have the standard for 6900 XTs again, the IR3 or 6950 XTs. There's really not that much difference. 35217 voltage controller from Infineon, which, international rectifier label on the part, but international rectifier is owned by Infineon for a while now, so it's an Infineon part at this point. Anyway, this is a 6+2 phase controller that was originally introduced with the Vega GPUs. And on 6900 XTs and 6950 XTs, it's typically in charge of handling the memory rail as well as VDDCI. It is, in my opinion, incredibly overkill for this application. Like GDDR6, what is it? 8 chips of GDDR6 don't pull that much power, and the VDDCI rail is literally one phase, right? Like, that should tell you how much current that rail pulls. Not much, because it's one phase. So, yeah, this is, it's the norm for 6950 XTs. It's just very, very overkill to use a controller like this for basically to handle just 2+1 phases. But yeah, you just see this on most 6950 XTs. I assume it mainly has something to do with the voltage regulation, the voltage regulator communication system that AMD has on their cards. Though admittedly, the NCP 81022 exists, so I'm not entirely sure why we don't see that chip more often being used for memory and VDDCI. But either way, ultimately, a slightly more expensive voltage controller is not going to make a big difference to the overall cost of a card that costs over $1,000, or around $1,000. It really doesn't matter. Like, the difference, if I had to guess, the price difference between an NCP 81022 and an IR 35217 is probably $1, maybe a bit more than that. Which again, just on a $1,000 card, that's not really going to make a difference. Anyway, so that's the control scheme. And now let's talk about the current handling capability thanks to those TDA21490 smart power stages. Now, the annoying thing with the TDA21490s is that they're entirely spec'd at 1.8 volts. I imagine they're very common on server hardware because they're actually kind of TDA21490s are actually kind of rare to see on consumer GPUs and motherboards. There's admittedly kind of a lot of 6950 XTs and 6900 XTs with them, but there are other power stages that are far more common. And yeah, so TDA21490s aren't actually they're kind of rare, and I assume a lot of them are probably used in servers because they are spec'd at 1.8 volts. And the reason why a lot of power stages get spec'd at 1.8 volts is because of Intel CPUs with fully integrated voltage regulators that run on 1.8 volts. So, yeah, anyway, the annoying thing with this is that at lower output voltages, these power stages should be producing less heat. Now, the crazy thing is, even at 1.8 volts, these produce so little heat, according to their documentation, which is public, by the way, that... I tried rescaling the numbers for 1.2 volts and I didn't want to believe them, so we're just using the 1.8 volt numbers because the documentation doesn't have a expected voltage scaling curve for the power for the heat output. So yeah, because even at 6950 XTs run on less than 1.2 volt or around 1.2 volts most of the time. So this is if anything, the VRM should be producing less heat on the power stages themselves, because in typical Infineon fashion, these are spec'd as just the power stage power losses. This does not include inductor power losses, and it doesn't include power plane power losses. But, since we're comparing against other 6900 XTs, which mostly use other Infineon parts, and 6950 XTs, which again use Infineon parts, there's not really a difference in the test methodology, so this isn't really much of a concern. Anyway, so for ambient overclocking, you can get 6950 XTs and 6900 XTs to hit around 350 amps quite easily. If you want to go past that, you need a lot of cooling because they do run quite hot. The chips are relatively thermally dense. And at 350 amps, this VRM should only be producing about 22 watts of heat, and that's again assuming 1.8 volts output voltage, 600 kilohertz, 22 watts of heat on the power stages, not accounting for any other power losses. So, for comparison, a reference 6950 XT should be producing about 33 watts of heat, and that's at 1.2 volts. Because I do actually have documentation for the TDA21472 that is spec'd at 1.2 volts. Yeah. So this right here is absolutely ridiculous. But, it makes sense. This is the, this is the only 90 amp smart power stage that I've ever seen spec'd for or with expected performance curves with a 97% efficiency as part of the sort of like achievable performance curves. So yeah, like in theory, this VRM should be one of the coolest running VRMs on 6950 XTs. Anyway, at 500 amps output, which now we're talking like LN2 overclocking territory, this VRM should only produce about 38 watts of heat, which is like, this is insane. This is absolutely ridiculous. Now this is past the peak of the efficiency curve. This is a lot closer to the peak of the efficiency curve. Like the VRM on this is probably one of the most powerful VRMs on a 6950 XT. Because there are admittedly like 13 phase and I believe a 14 phase VRM using these same power stages from ASRock. And the 13 phase I think is Sapphire's Toxic card should be using that. Yeah, like other than those two, like this is ridiculous. For comparison, a reference card should be producing about 60 watts of heat at 500 amps output current, and that's at 1.2 volts. So yeah, like this VRM right here, just like at least on paper, it's like insane overkill. So yeah, now. So yeah, current handling capability wise, the VRM is just ridiculous. Also, since these are smart power stages, they integrate temperature monitoring, current monitoring, overcurrent protection, over temperature protection. I believe these also have short circuit protection, but based on my past experiences with a TDA 21472, I don't trust the short, like if I should have probably written, no, my notes do say these have short circuit protection. I don't trust it because I've had a TDA 21472 fail high side MOSFET to output. Yeah, that wasn't fun. Anyway, let's take a look at the back of the card. Because now let's talk about the output filtering. And Gigabyte, and this is the part of the card that I am like very, very confused about. Because like, it just makes it like, it's not bad. It's just really confusing as to like why they did what they did. So this is so like obviously you have a bunch of V-core filtering over here, and this isn't the entire V-core output filter. This is part of it, but this is the bulk capacitors of the V-core output filtering, right? Like over here, you can see that you have the split in the power plane for VDDCI, and then you have more V-core up here. And technically, I guess I missed the fact that we do have this capacitor over here. Oh wait, that's another 330. Anyway, okay, yeah, so I'll just add that to the one in my notes, because my notes only counted the ones on the back, and then it's like I realized starting this video that, wait a minute, this is V-core. Anyway, so the very strange thing about the output filtering on this card is a typical, so a reference 6950 XT or 6900 XT has 8 470 microfarad bulk capacitors for output filtering. These are SMD aluminum polymers, so very low ESR, very low ESL. Great capacitors, like you can't really get anything better in terms of in terms of ESR and ESL, you really can't get anything better without going for like multi-layer ceramics, and multi-layer ceramics get very expensive very quickly because you can't get them in high capacitance unless you get them in like a 1210 package, and the 1210 package actually has similar like frequency response to a 2917 aluminum polymer, so they're actually kind of pointless. But anyway, so these are great capacitors, but 6900 XTs and 6950 XTs don't you really use that many of them. Like 8 470 microfarad capacitors is really not that much bulk capacitance for a GPU. Now, the interesting thing about this Gigabyte card is that Gigabyte basically took the reference output filtering configuration, or like the bulk output filtering configuration of a reference card, and then for some reason they added 4 330 microfarad aluminum polymers to that. And I do not get this. Like, this is such a, like, so this helps a little bit, I guess. The thing I'm confused about is like, why are these a different value? Right? Like these 330 microfarad capacitors. And what I'm talking about is this capacitor right here, this capacitor here, this one, and wait a minute. Did I screw up? 470, 470, 470, 470, 470. Wait, I did count them all. Wait, no, that's 1, 2, 3, 4. Right, and then you have the fourth one on the back of the card. I mean, front of the card. So yeah, and then you have this 330 over here. Like, those are the only 330s on the entire card, which basically means that in order to get these on there, like, this is a second component reel in the manufacturing process. Like, I really don't get why, you know, like first of all, I don't think 330 microfarad capacitors really make that much of a difference. Without taking an oscilloscope to the card, I'm not certain of that, but just based on my past experience trying to mod GPUs, like doing cap mods on GPUs, 330 microfarad capacitors just, it doesn't really sound like it's going to achieve anything to me. Okay, like, I'd be very surprised if this made much of a difference. Like, you might be able to measure it. Maybe it slightly reduces the overshoot. I don't think it would significantly affect the undershoot on a load insertion transient. And so consequently, this really shouldn't impact overclocking like at all. And the thing I'm wondering is, why didn't they just do like 470s instead? That would get them like if there was like a certain bulk capacitance target that they wanted to achieve, like this would be the cheaper way to do it. It would probably achieve, like, I'd imagine in terms of, like, if you measured voltage regulation performance, I imagine it would be basically the same, if not exactly the same, because, like, yes, more smaller capacitors is better for your ESR and ESL, because more capacitors in parallel means those effects get reduced. But, you know, we're literally talking about 4 capacitors versus 3 capacitors. We're not talking, like, one big capacitor, like 10 big capacitors versus like 30 smaller capacitors. That's a significant difference. This is 4 versus 3. These are 330s. So, like, this is an upgrade. Very technically, this card does have more bulk capacitance for output filtering than a reference card. I don't really think it makes much of a difference, and I'm very confused as to why they didn't just use like 470s. Also, they added all these extra pads. Like, I feel like it would have been neat if they had just fully populated it with extra 470s. That would have probably actually made a difference, but yeah. Anyway, so yeah, Gigabyte decided to do this. I think it's kind of weird, but you know, it doesn't hurt anything. It's just like, but why? Like, does this actually achieve anything? I'd love to see an oscilloscope comparison of this card against like a reference card, because I really don't think this makes much of a difference, if any difference. Anyway, the other thing that I wanted to talk about in terms of capacitors is the input filtering, because this is the same as what they had on the 6900 XT. I don't believe I ever did a full-blown PCB breakdown video of that card, and I don't particularly like what Gigabyte has done with the input filtering on the card. Because basically, on a typical 6900 XT, your input filtering inductors would be 190 nanohenries. The ones that Gigabyte is using here are 680 nanohenries. And basically, this means that these inductors block more switching noise from the GPU than what you normally get on a 6950 or 6900 XT, or 6800 XT for that matter. They're all basically the same. And so this means that basically with these higher inductance inductors, in theory, this card should be putting a lot more load on its own bulk capacitors for 12 volt like input bulk capacitors. So that would be these like 16 volt capacitors over here and this one. And also, of course, the multi-layer ceramics that are being used for like that are filtering the 12 volt supply to the power stages. Like these capacitors are on the card because when the GPU core suddenly needs to tries to pull in a bunch of current, or the VRM will typically switch on multiple phases at the same time. And so suddenly the VRM tries to grab a bunch of energy. And these bulk capacitors are basically there to provide that energy for the VRM in such a scenario. Um, by putting these higher inductance inductors onto the card, Gigabyte is basically limiting the ability of the card to grab energy from your power supply quickly. It basically slows down how quickly the card can request current from the GPU, which means that these capacitors need to do more work. And in typical 6900, like 6950 XT, 6900 XT, 60, you get the idea fashion. Uh, there's not much bulk capacitance here. Just like this is eight 270 microfarad bulk input filtering capacitors. For comparison, a lot of high-end GPUs, especially NVIDIA GPUs, which are notorious for extremely sharp transients, those have one bulk capacitor per power stage. It's not even per phase, it's per power stage. And so, yeah. Now, admittedly, the side effect of having, not great input filtering is that basically the card has slightly worse output voltage regulation, therefore the overclocking is a little bit worse than it would be if you had more bulk input capacitance. And when I say a little bit worse, I mean like 10, 20 megahertz, maybe 50. So it's not like it's going to be a noticeable difference. It's just kind of like weird. Um, that like modern high-end AMD GPUs just have like no input filtering compared to old AMD GPUs, which had less drastic transients because they didn't have a hyper aggressive boost algorithm. So yeah, I'm not really a fan of this. I'm not really a fan of I'm not a fan of this on this card, but I'm not a fan of the capacitor configuration on basically any 6950 XT or 6900 XT. But then, like, especially the higher inductance inductors is like, well, I'd love to see what what the effect of these looks like on the oscilloscope, but I am very much not a fan of those. Also, they probably slightly increase the power losses between the power supply and the GPU because higher inductance inductors, unless they're physically larger, generally come with more DC resistance than lower inductance inductors, because the way you get more inductance is you put more turns of wire into the same amount of space, and that generally means the wire needs to be smaller if you want to make more turns with it, right? Because there's a limit to how much wire you can coil in a footprint, like inductor footprint this size. So yeah, ultimately, I find this card very interesting. Like, I find this card very interesting in the sense that I would love to see a lot of measurements from one of these, right? Input filtering, like oscilloscope measurements, comparing this to a reference card in terms of like, how much switching noise do we have on like this side of the inductors? How much switching noise do we have on the power supply side of the inductors? How much, how good is the voltage regulation on the output of the VRM? Maybe that's why this card has slightly more bulk capacitance, because Gigabyte is like, well, on the output, because the input filtering is not great and arguably maybe worse than a reference card, thanks to those higher inductance inductors. You'd have to measure that, but um, I'm suspicious of that, and yeah, and then like as far as like actually buying the card goes, I mean, you can get cards with admittedly not VRMs that might be this efficient, but VRMs more than capable of powering a 6950 XT, but also with fuses on every single input. Dual BIOS isn't that special. There are cards with better output filtering configurations. There are cards with better input filtering configurations. And so while this isn't a bad 6950 XT, I would consider it more like an interesting experiment in 6950 XT PCB design because it's very different to most 6950 XTs. And speaking of things that are different, they've also gone with lower inductance inductors on the memory VRM. And I'm really not sure why, because again, like powering memory generally isn't very difficult, so you shouldn't like this could arguably improve the voltage regulation on the output of the memory VRM, but um, like, why would you even bother with that? Because it's the memory VRM? Like, this isn't GDDR6X, and there's not that many memory chips on here. But, yeah. Oh, actually, the one thing I forgot to mention is, like, if you have this card and for some, and, like, if you do have this card and you want to, take control of the VRM using an Elmore EVC2. The I2C header is over here. It's this thing. I don't know which order the pins are in, but basically if you plug it in backwards, it just won't work. So, you can, like, you plug it in once, it doesn't work. You plug it in the other way, it should start working. So, yeah. Anyway, so that's my thoughts on the card. Just a sort of strange take on a 69, or very different take on a 6950 XT. Would be very interesting to see some measurements from it. I wouldn't be rushing out to buy one of these because I don't really think like it's not a card that I would outright avoid because like most 6950 XTs have a bizarre input filtering configuration. Or more like lacking input filtering configuration. So I don't really think that's much of a, like, that doesn't really count against this card in my opinion. But yeah, like I also don't consider this like this is certainly not the best 6950 XT PCB you can get as far as I'm concerned. So anyway, that's it for the video. Thank you for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's a link to that down in the description below. There's also the AHOC Teespring store where you can pick up shirts, stickers, hoodies, posters, the usual YouTuber merch. Actually, and also as of, well, I also have a Bandcamp. So yeah, there's a link to my Bandcamp down in the description, and Teespring and Patreon. And if you'd like to check any of those out and, use them to support the channel, that would be much appreciated. And that's it for the video. So thank you for watching, and goodbye.